Good morning, good afternoon, and good evening, depending on where you guys are at. And I'd like to start by sending out a warm welcome to everyone who's joining us today for the SNIA Network Storage Forum sponsored presentation. In today's presentation, we'll be discussing next generation interconnects and their critical importance. Before we jump into this presentation, though, I'd like to just quickly cover a few items on the BrightTalk user interface. First, we get a lot of questions for people asking us if they can download the slides. And you will see in the bottom a tab for attachments, and you can download a PDF of the slide deck there. Next, this presentation is going to be heavy on the graphics, and some of the text also might be slightly small. So I'd recommend enlarging your viewing area to full screen, and this can be accomplished by clicking on the double arrows on the lower right-hand corner of the presentation. I'd also like to encourage everyone to make this presentation interactive by asking questions of your presenters. You'll find a chat box in the lower right-hand corner of your window where you can type your questions. But because we do have a full agenda today, we may have to ensure that this completes on time, and we'll be saving the questions to the end of the presentation. Often we have such great participation that sometimes we can't cover all the questions in the allotted presentation time. If this does occur, we will be releasing a blog to the SNIA website that contains all the questions with their corresponding answers. Also, we frequently get, finally, we do request that you rate this presentation when we're finished, and you'll have an option of rating it between 1 and 5 stars, with 5 being the best. We also appreciate any comments and suggestions, because we do value your opinion, and it does help us improve the quality of future presentations. Now let's just jump in real quick to today's presenters. My name is Tim Lustig. I'm going to be your moderator, and with me today we have 3 highly qualified presenters. First up is going to be Kent Lustig. Kent is a principal engineer at Intel and has over 30 years of experience with Ethernet PHY standards, and is also the co-chair of the High-Speed Networking Subcommittee in the Ethernet Alliance. Brad Smith will follow Kent, and he comes from NVIDIA Networking. He's the director of marketing there. Brad has over 30 years of a diverse experience, including working at Intel, as well as in research and analyst positions. And then closing out the presentation today will be Sam Casas. Sam comes from Amphenol, where he is the Director of Standards and Technology. And before we jump into the presentation, I just want to cover something real quick about our sponsor, SNIA. SNIA is a global industry association who's chartered in the adoption of storage networking. Within this charter, it is to remain vendor neutral, and we do have a participation from over 100 different industry-leading organizations with over 2,500 active contributing members. As I mentioned, everything will remain vendor neutral. As this is a global organization, we reach over 550,000 end users worldwide and focus on standard adoptions and education. And 2 more slides before we jump into this presentation. First one here, a little bit more on SNIA. This is basically a framework. It tells you about the technologies that we cover. Everything from protocols to storage networking to storage architects, including virtualization, software-defined storage, and aspects of securing data. And the final slide here is something that our lawyers make us put in here. And this shouldn't be any surprise to anybody. It's standard legal talk. The material that you're going to be seeing today is copyrighted by SNIA, and the use of the material within the presentation is permitted as long as the slides are reproduced in their entirety and SNIA is referenced as a source. Please be aware that there is no warranties expressed or implied by the information presented, and you are using it at your own risk. With that done, we'll jump right into the agenda. We got a full plate, as I mentioned today. We're going to go over a lot of different aspects of the pluggable and connectors and media types, as well as the copper and optical media. We're going to talk about the development of 25, 50 gig, and 100 gig, talk about the different standards that are out there, and then why the different types of cables matter. We'll jump into copper cabling and transceivers, cover signal modulation, optical connectors, and talk about why all the variety is necessary, and even get into some real-world use cases. And with all that said, I'm going to go ahead and turn it over to Kent to take over the first part of the presentation.
Great, thank you very much. I appreciate the introduction. My name is Kent Lustig. I'm employed by and affiliated with Intel Corporation, and I will be covering common pluggable connectors and the media types. Thank you for this opportunity to be here today. For my section, we're going to discuss pluggable connectors, because pluggable connectors come in a variety of sizes and lane widths. The 1-lane and 4-lane connectors are the most common. However, the 8-lane and 2-lane connectors are coming into deployment today, and we see a path to 16-lane on the horizon. There's both copper and optical media used in networks today. Now, copper is focused on cost and short reach, whereas the optical medium step in for longer reaches. And then we're going to talk about 100 gigabit and 25 gigabit Ethernet, specifically the 3 types of 25 gigabit Ethernet that exist today. This graph shows the history of pluggable networking connector form factors. To orient you on this slide, on the bottom in the x-axis, you'll see a timeline from 2001 out to today, which is the yellow star. In the vertical axis, you'll see the number of lanes. It all started in 2001 with the SFP connector, and over time, the industry recognized a need to move to 4 lanes. So the connector was expanded to QSFP, which is our 4-lane connector. And again, over time, industry saw a need to move to 8 lanes, which resulted in the birth of the OSFP and QSFP form factors, as well as a new 4-lane connector called the micro QSFP. And this resulted in further development in 2-lane connectors, the DSFP and SFPDD, as well as in the top right-hand corner, a path towards the OSFP XD, which is a new 16-lane connector on the horizon. So you'll see that when we talk about pluggable networking connector form factors, that there's a variety of different lane widths as we look across time. Let's take an example of SFP. How is SFP used? The SFP itself is a 1-lane connector, as we saw in the previous slide. And this connector can be used for copper cables, can be used for optical transceivers, or even base T devices, pluggable media, if you will. On the right-hand side, you'll see a picture of a representative networking card with an SFP form factor connector, of which either the top optical transceiver can be plugged in, or bottom, a passive copper cable can be inserted. That allows the end customer and the user to choose the media for their particular application. Now, sometimes we'll hear different terms, SFP, SFP+, SFP28, and what I want the audience to walk away with is that SFP is a generic term, but generally means the 1 gigabit rated connector. We have the SFP+, which is a 10 gig lane rated connector, and we have the SFP28 rated connector. More of these details will be covered a little later in the presentation by one of my co-authors. The other common connector form factor is the QSFP, and this stands for Quad Small Form Factor Pluggable, QSFP. It's a 4-lane connector type, and 4-lane means that it holds 4 lanes of media. It can be used with a 4-lane physical PHY, as shown on the left-hand side, where all 4 lanes go to the cage, or in the middle, you can see that this is 4 different single-lane PHYs that go to the QSFP cage. So this can be used in a couple different ways. The QSFP itself is used for many different networking fabrics, such as Ethernet, InfiniBand, Fiber Channel, SAS, OmniPath, and various other proprietary protocols. This is quite a popular connector. And it should be noted that this is not a CR4 connector, nor is it a 40G or 100G based connector. It is a QSFP connector. And we'll go through some more examples of these later on in the presentation. One of the most common media types is the twin axial direct attach copper cable, also known as DAC. And DAC cables come in 2 different kinds, if you will, at a high level. There is the point-to-point, which is generally a 1-to-1 connector, okay? And then we have on the right-hand side, the breakout cable. This is also a passive direct attach copper cable, and it's point to multi-point. So it's 1 point to 2 connectors, 4 connectors, maybe 8. And when we talk about direct attach copper cables, we realize that there's 2 classes. There's the passive direct attach copper cable, in which it's a simple construction, with a high-speed twin axial conductor between the two connector ends, but there's no active components inside the assembly. There's no active drivers or retimers. Now, if we compare and contrast that to the second class, what we call active copper or active electrical cables, ACCs or AECs, these devices themselves have active devices like retimers and redrivers inside the connector that can be used to help increase the performance or increase the reach of the copper cable. Another common media type are pluggable optical transceiver modules. On the left-hand side, you'll see a pluggable transceiver. On the right-hand side, you'll see an active optical cable. If we talk about the pluggable transceiver on the left-hand side, it's a module itself in which the fiber can be separated from the pluggable transceiver. In this case, there's an electrical interface to the host. There's a separable interface so that the fiber can be physically disconnected, and we have an optical fiber cable. It may have one or more parallel lanes in each direction representing transmit and receive, depending on the physical layer specification. The active optical cable, on the other hand, has a non-removable optical cable. The whole fiber is connected directly to the connector assembly itself and represents a captive interface to the fiber medium. And one of my co-authors will go through the particular use case inside of a representative data center a little later in the presentation. For optical fiber, we have two main types of optical fiber. We have the single mode fiber and multimode fiber. And here's a quick high-level overview of the difference between the two. The single mode fiber has a very narrow core in which the light travels without bouncing through the core. It's typically represented by a yellow color fiber through industry convention. And we compare and contrast that with the multimode fiber shown at the bottom here, in which the light is able to bounce around inside the core, and it's represented typically by an aqua green fiber color within industry. So we have a single mode and multimode fiber shown on these slides. Let me transition now to talk about the development of 100 gig and 25 gig Ethernet, because 100 gig is really being deployed in quite broad volume, and we're seeing a real surgence of 25 gig Ethernet coming into various applications. This really started in 2012 when industry recognized the need to move from 10 gig per lane class SerDes to 25 gig per lane SerDes. 4-lane media was already common because we had 40 gig CR4 and 40 G KR4. We already had these 4-lane interconnects. Therefore, there was a logical path to 100 gig by taking this 4-lane medium and increasing the rate from 10 gig per lane to 25 gig per lane using 25 gig SerDes. As 100 gigabit Ethernet was deploying, there was strong industry from a number of companies inside the industry to use 1 or 2 lanes of these 25 gig SerDes for server connections. And first came the Ethernet Technology Consortium version of 25 gig Ethernet called 25G base CR1. Then came the IEEE 802 versions of 25 gigabit Ethernet, the 25G base CRS and 25G base CR. There are 3 versions of 25 gigabit Ethernet. They are different from each other, and we'll cover those details in the next slide. Starting at the top, there are 3 25 gig PHY cable PHY types. The first one is IEEE 802.3 25G base CR. It supports 3 different FEC modes for your particular application. It has cables up to 5 meters, 5 meter reach. When we look at 25G base CRS, this is a subset of the 25G base CR PHY defined by IEEE. It doesn't support the Reed-Solomon FEC. It only has 2 FEC choices. And it should be noted that this particular mode is compatible with the consortium's 25G base CR1 when no FEC mode is chosen. This gives you a 3 meter reach of the cable. Last but not least is the Ethernet Technology Consortium 25G base CR1. It's compatible with the IEEE 25G base CRS up to a 3 meter cable. But the net takeaway is that there's 3 25G cable PHY types. Now, this is important to remember for 25 gig Ethernet deployments because there's 3 different types of cables that can be used. There's a 25GL, a 25GS, and a 25GN. They have different reaches allowed by the specification limits, and they support different FEC modes. And this matrix illustrates the cable type mapping to the supported PHY types. And I would encourage you to take a look at this chart in great detail to recognize that some cable types support all PHY types, and some cable types only support one PHY type. So please take that into consideration as you're deploying 25 gig Ethernet. The cable type matters because the choice of the cable affects the auto negotiation process and affect choices available between 2 endpoints. And the cable choice, the cable type itself, might be interpreted differently by each vendor and could result in link-up issues. You'll need to know what kind of cable you have, and please note that visual identification generally is insufficient. We'll have to do additional work looking at part numbers and next level of analysis if your link does not come up or give you the performance that you anticipate. So in summary, pluggable connectors support both copper and optical media. The copper media can either be passive or active. The optical media uses different types of fiber, whether it's single mode fiber or multimode fiber. And the transceiver can be separable or captive of the fiber. And we talked about 25 gig Ethernet and the copper cables. They have a special relationship. There's 3 types of Ethernet PHYs and 3 types of cables to consider in your 25 gig network. That's what I have for you now, and I would be happy to transition this over to Brad Smith for the next section. Brad.
Smith, I'm the Director of Marketing for the LinkX cable and transceiver line at NVIDIA. That's for Ethernet and InfiniBand. And I'm going to build on some of the concepts that Kent talked about. Let's see here. So there's, in the data center, there's 4 basic types of cable and transceiver products. You have a direct attached copper, basically wires, maybe an EEPROM inside, very simple, very low cost. But as you go faster with faster line rates, the wires act more like antennas, and the signal gets radiated into space. So the industry created an active copper cable where we put a chip inside that it's either a DSP or a pre-emphasis chip of some kind that boosts the signal. And we get a couple more meters out of it. You can see 5 meters at the top at 25 gig NRZ and 7 meters at the bottom with ACCs, or active copper cables. On the right, we have optical transceivers. You see the various types of optical connectors. And they're all different types for different applications, but you can disconnect the fiber infrastructure from the transceiver. And then in the middle, we have an active optical cable, which is where we take the optical cable connectors and cut it off and glue it inside the transceiver, and it becomes an active optical cable. And it looks pretty much like it shadows the DAC and active DAC cables in terms of their structure. Here's sort of the 1x, the 4x, a 2x splitter, and a 4x splitter that you find in direct attached copper. You also see the same thing in active copper, again, a couple more meters. And you can see that it shadows it in active optical cables as well. So pretty much the same thing, only that maybe go out to somewhere between 30 and 50 meters, depending on the use case. And then on the right, you see multimode, which is denoted by the aqua color. And that usually is tied to the multimode fiber, multimode optics, and the 850 nanometer wavelengths. And then the single mode, which is typically in the 1310 nanometer range. And that's denoted by yellow. And you'll see either the blue or the green on the connector. So the colors have meaning, except for the pull tabs, which is sort of a free-for-all. So this is what's inside a DAC cable. It's basically a bunch of wires with fiber with a foil or a mesh shielding. In the connector end, you'd have the metal shell, a QSFP 28 or something similar, and a printed circuit board. And on that, you'd have a cable ID EEPROM, and that's used to just tell the switch or the network adapter the protocol, the length, the speed, and so forth, different parameters used in the signaling. But that's it. That's pretty much all that's in there. So it's pretty simple. Differential signaling. So you have roughly 3 wires for every direction. So if you have a 2x400 gig DAC cable, it would have 48 wires inside. So 3 wires in each direction, which is 2 plus a ground, and 8 channels, 2 directions, 3 wires, 48 wires. So it gets pretty crowded. But that's a DAC cable. It's 0 latency, 0 power consumption, the lowest possible cost. It's simple, very reliable because there's not much in it, and you get somewhat of a longer reach at the slower speeds. But as you see on the left, in red, things get pretty short as they get as the speed goes up. Disadvantage is that it's heavy, it's bulky, and it gets shorter with the faster line rates. So here's an example of the active copper cable, and you see it looks identical. It's just the reaches kick up, and it consumes some power, and going through the electronics induces some latency. So there's some disadvantages there, but you get the boost to keep the cost down. It's a little bit more expensive than just DAC cables, but a lot less expensive than active optical cables. So it kind of fills in that gap. This kind of a picture would kind of show you just the top of the rack of several racks. You can imagine this is gets very heavy. Early builds with all DAC cables, people put them on raised floors infrastructures, and they come in the morning, and all the racks are tilted and crash through the floor. So it's it can get very heavy. It's bulky. It's it's difficult to manage this. So you can see by the orange cable there, that's probably an active optical cable. And you can see how much thinner the orange is to the black of the DAC cables. So the faster you go, the more the signal acts like a radio antenna and just broadcasts off the wire. So you end up putting more and more shielding on it. If somebody could put their system on mute, I appreciate it. Whoever just sneezed. So you have roughly 7 to 10 meters at 1 gig or 10 gig. And you can see as you go down the stack, the black lines get thicker and thicker. And then we break into 2 wires, 2 cables. And then at 100 gig PAM4, you're somewhere around 1 to 2 meters. And the industry is still trying to maybe boost that up a little bit, but we're somewhere in that zone. But we go from 7 to 10 meters down to roughly 2 meters. So you can imagine the next stop is going to be even shorter. So right now, this is about the length of, let's say, from the floor to your armpit, and pretty soon it'll be maybe the length of from your hip to the floor. So it's end up putting the switch in the middle of the rack and going up and down, and so the DAC cable starts to dictate how the network is being configured, and that's probably not a good thing. So one of the things we did is, as an industry, is we started off with 1s and 0s. A long time ago, we would put a 0 and then a data bit and a 0. It was called return to 0. And then we figured out how to trigger on the edges of the rise times, and it became non-return to 0, or NRZ, as it's known today. And that's the basis of the digital age, the 1s and 0s that we're all familiar with. But as we go faster and faster, to make the basic clock rate run faster means everything gets more expensive and complicated and shorter. So the industry said, well, let's stack 2 bits on top of each other. We'll call it pulse amplitude modulation at 4 levels. So that's what you see on the 50 gig PAM4 line. And you can see it's the same clock rate as the previous 25 gig NRZ. So they're able to keep the cost down. But now we have to go and boost the clock to 50 gigahertz, 2 bits per clock. So that gives us 100 gig PAM4. And you can see it's getting pretty tough. If you look at the signal eye diagrams on the right, it's getting pretty tough to pick out the data from the noise. It's just getting to be a big blur. So a lot of the electronics is moved from just a simple clock and data recovery circuit, which might take less than a watt and a few nanoseconds to get through, to using a digital signal processor, which is actually a microprocessor to sort out the signal and run algorithms against the data. So it's getting much more complicated. The Buzzword-ology of optics is a language in itself. I've been told I can speak for 5 minutes and use 3 words found in the English dictionary. But this is the root, the SFP, the small form factor plug, as Kent mentioned. You can see if it's in the baby finger of my hand, that's roughly the size of it. I got big hands, but it's got 1 channel. A channel is a down and back. It's like a road, 2 directions. And then we have 4 channels, a QSFP, quad. Then we put 2 rows of electrical pins on the end. It's called a double density. And that's used for 400 gig and soon 800 gigabit Ethernet. And then there's a competing version, which is the OSFP or Octal SFP, which has 8 channels. And you can see by the size of it, it's about the size of a small banana. It's not small at all, even though it's got small form factor plug in the name. And that also has 8 channels, but it's 8 channels across the end instead of 2 rows. And there's a new one coming called the OSFP XD, which has 16 channels with 2 rows of that as well. So the ending of the SFP is the speed, the maximum speed. Generally, the telecom uses like 28 and 56. Ethernet might use 25 and 50 gig and so forth. So it's really a metal shell, and the 56 or 25 or 28 is just basically the maximum frequency that the shell can keep inside and keep the noise from going everywhere else. So that's the secret decoder. Here is a picture of the different QSFP starting at the top, and we use that for 100 gigabit Ethernet, and then 200 gig, it got a little bit longer, a little bit more heat capacity, that's QSFP 56. And we have the 400 gig for the QSFP DD, and then just recently the committees have just introduced the QSFP 112. That's 4 channels of 100 gig PAM4. And then we jump to the OSFP. You see it's much bigger down the bottom with, you can tell by the purple lines there what's going on. But the one at the bottom, the OSFP XD with 100 gig PAM4 will be able to do 1.6 terabits per transceiver. And at 200 gig PAM4, 3.2 terabits per transceiver. And it wasn't too many years ago when we had a 3.2 terabit switch, and now we're going to have a transceiver with that speed. So it's getting, you know, this is a progression that's probably not going to stop. It's going to keep going. And on the right, you see the SFP 28 and 56. They're almost the same. And then the DSFP and the SFP DD with 2 channels at below. And those are fairly new in the marketplace as well. So this is the OSFP. I kid that the yellow tab is a trailer hitch. It's not really a full tab. But you can see with the different switches, if you put 64 of these into a switch, you'd have a 408 terabit switch. So the bottom line is you're going to see pluggables around for a long time. In spite of all the, you know, the trade shows and the different groups touting co-package optics. Co-package optic is very complex, and if you have a transceiver that blows, it's not easy to fix. But with pluggables, you can see that it's just like it has been for the last 10 years. So it's going to be around a long time. And the OSFP XD, I think, has a top rating of 30 watts. So it's getting interesting. There's two basic categories of fibers. You have the multimode, which has a big core diameter, as Kent mentioned. You can see by the little picture on the lower left that the light pulse, which consists of a bunch of photons, will have each photon will take a different path. And the signal will basically, the further you go out, the photons will take different paths through the fiber, so they arrive at different times. So the signal stretches out and gets lower in intensity. So the IEEE says, okay, we're going to call it, if you put two patch panels in between, 100 meters. And that's what's the standard is for that. Is you can go a little bit longer. You get some engineered systems. You can actually go up to 400 meters, but it gets very complicated, and you got to buy special parts and so forth. So it's called short reach, or SR. So you see the transceivers with SR, SR4, SR8. And then you have the longer reach things. The yellow is the mnemonic to remember is the Beatles, the yellow submarine. So you use the color yellow if you're getting in a submarine and you're going to travel from San Francisco to Hawaii. So that's how you remember that. And then the aqua color is the other one. So that's one way to remember it. But the telecom industry uses a single mode fiber, and it has a very tiny optical core. So when you send the signal down there, it stays together. It's about a 7 or 9 micron core, which is about the size of a red blood cell. And you have to align this to the lenses and the detectors and lasers, plus or minus a couple of coronaviruses. So it's expensive to build, and it's all robotic built, but you can do 100 kilometers with this. So it's good for the longer reaches. So each of these has a place in the data center. We have in the past we've used the multiple push-on optical connector for the 8 fiber parallel. There's actually 12 fibers, but we use 4 transmit and 4 receive. The reflected energy off the end of the fiber is fairly small because the core is very large. But when you go to single mode, this becomes a problem, and the reflected energy off the end of the fiber bouncing back is sort of like when you look through a window. You see the car across the street, and you see your face in the reflection of the window. Well, those reflections ring back and forth and just interfere with the data signal. So it's becoming an issue. So the industry is moving to what's called the angled polish connector, or MPO APC. And you'll see these in the 400 gig SR8 and all the 100 gig PAM4 stuff. And it basically puts an 8 degree polish on the end, so that you see in the red that the reflected light just kind of dead ends into the cladding and just turns into heat. So this is being used for all of the high speed stuff coming up. So they are not compatible with each other. The one on the left is flat polished, and the one on the right is angled polished. So just be aware that that's coming. So you end up with a wide array of different cables and transceivers, and all different lengths. Each one of these has a 0.5 meter, 1 meter, 3 meter, whatever. So there's a zillion products and a zillion SKUs. And as Tim started to mention, some of these have, at the 25 gig, they have the CA-L and S and N for FEC and no FEC and so forth. So this gets to be a very complicated set of requirements. And on the right, you see there's a zillion types of transceivers. And part of the reason is that you have so many different transceivers is the DAC cable on the upper left you could buy for $20. And a 40-kilometer transceiver down in the lower right might cost you $20,000. So you have a wide array of different price points for different reaches that you go. And the faster you go, and the further you go, the more complicated and expensive everything gets. So that's why you have all these different parts. Here's the secret decoder for all the different buzzwords, DR4, FR4, LR4, all this kind of stuff. I'm not going to go over it, or it'll be in the PDF if you want to look at it. You have to learn to speak this language if you want to talk optical, so it's kind of funny. But anyways, and there's a secret handshake that goes with it. This is how you'd use a multimode optics. You go from a server through a network adapter, transceiver up to a switch and back down to a flash, SSD, or hard disk drive array. And this is typically how it's used. In the US, this typically is done with DAC cables I've shown previously, but in Asia, a lot of folks like to separate the servers and the storage, and they'll kind of run it along the face of the system row. So they use either AOCs or transceivers. AOCs look just like this, only it just doesn't have that little connector on the end. And then you're typically going to use the AOCs and transceivers that go from rack to rack, usually in the above the system. You have some kind of cable tray, so you kind of throw it up there, and that's very popular because it's so much cheaper. It's an electrical test instead of an optical test. Electrical test for an AOC, just plug it in and watch what the switch tells you. For an optical test, you need a $500,000 worth of piece of equipment and a test operator to test all kinds of conditions. So the transceivers, a rule to remember is a single transceiver is priced almost the same price as a 2-transceiver active optical cable. So it's that much of a cost savings. And then for the single mode optics, you could do the same thing. Some companies use single mode everywhere, so they go, top of rack down to the servers with single mode optics. But it's generally used for the longer reach capabilities. 500 meters, 2 kilometers, the most popular. And you see the different terminologies. The SR is a short reach, DR is data center reach, 500 meters, and FR4 is the 2-kilometer far reach. LR is long reach. So that's how all these are used. There's another way of looking at it, sort of starting in the left, DAC in the rack, up and down. AOCs sort of between the racks and maybe going up and down in some cases. And then the transceivers, where you have the fibers disconnected from the transceivers, and maybe runs in the wall or piping or under the floor or in the ceiling, that kind of thing. So you disconnect the fibers from the transceivers. That's where you use the SR, SR4, SR8 type transceivers. That might go over the length of the row, or maybe between 2 rows or something like that. And then to go from maybe an end of row or maybe some type of aggregation switch going across the data center to maybe a leaf spine network. So you're going to use the DR4, FR4, or LR4 in those cases. Usually LR4s go out to the router. Here's another way of looking at it. Down below, you got all the compute and storage elements, DAC in the rack, and coming out of the top of rack switch with the Aqua multimode, either AOCs or transceivers, to a leaf switch. And the leaf and the spine, which is the next set of switches up above, this forms a sort of a superhighway. And this is so that the lowest point on the rack on the left, the bottom of the rack on the left, get to the bottom of the rack on the right by just going up to that superhighway. And boom, boom, you can get there with maybe 3 switch hops. So that's kind of the goal, is to reduce the number of switch hops if possible. And you can see the different types of transceivers where you typically use, say a hyperscale guy would have a 2-kilometer superhighway. Those fibers are 2 kilometers for the long reach. And the rough 6 dB link budget, so they can push through a lot of patch panels and so forth. But then you're back to DAC cables at the top, because the spine and super spines are typically in the same rack. And then you might go out to the core router with an LR4 or some kind like that. So that's kind of the basic network, but this is kind of where most of the traffic is, and most people are surprised at this, but most of the traffic is in the rack. I mean, think of it, that's where the computer and the disk is, so, or the storage. So it's going to be chewing on the data, going up and down, and maybe you go across a few different racks, because your data or your computers are spread out, but that's pretty much where most of the traffic is. And then going between the different racks, it's much less, and then even less going out to the internet. So here's just a couple more slides. This is a typical data center picture. You can see the cable tray in yellow at the top. You're going up and down the rack with DAC cables, and you might have a splitter or a 2x splitter or 4x splitter, or even a straight, depending what you want. And then if you use active optical cables, you're typically going to run across the top in that cable tray. Or if on the right, that's a supercomputer, you can see it's all active optical cables, because they want to deal with the connectors. So it's a little bit different between an enterprise Ethernet system and a HPC InfiniBand system. And then you might want to come out of that top rack switch and beam it out to another cluster, out to the router, go out to the internet or something. So you're going to use a single mode at that point. And here's the largest supercomputer in the world. It's the size of 2 tennis courts, has over 100,000 active optical cables in it. It's all active optical cables, and it's just one throbbing computer, and it handles one compute task at a time. They take a job and they dice it up into tiny pieces, broadcast it out to all the compute elements. They compute it, send it all back to the answer, go to the next. And then here's a hyperscale data center. The picture on the left is in one direction. It actually is the same if I flip it's in the other direction, but you can't even see the end of the building. It's enormous. And the biggest data centers being built is 11.3 million square feet, which is 15 of these things. And you can see the one on the right, that's a Facebook data center, and they stretch these things out quite a wide away. So you have a lot of single mode optics involved in here. So what I told you is about the DACs, ACCs, AOCs, multimode, single mode transceivers, why I have so many different types, what they are, and kind of where you use them. Quick look at some of the higher speed things, and where you use them in all the various systems. So with that, I'll turn it over to Sam.
Thanks, Brad. And again, my name is Sam Kosis. I'm employed with Amphenol Corporation, where I'm a Director of Standards and Technology. So far we've talked about the importance of the interconnect in terms of implementation, either with passive copper or optical examples, as well as application, either long reach or short reach, or switch to switch or switch to server application. But I wanted to change gears a little bit and talk about the importance of the connectors and cables with respect to the structures that make up the interface. The pluggable interfaces are a breakpoint in the data path that must sustain multiple mate and unmate cycles and maintain functionality with multiple supplier solutions intermated. So in terms of defining the mechanical interface, we typically use terms like fixed side and free side. The fixed side defines the connector that accepts its mate upon mating. This is commonly referred to as the receptacle or the socket. The free side defines the connector that penetrates its mate during mating. This would be like the plug or module, paddle card or edge card in common nomenclature. So during mating, the free side contact travels across the fixed side contact to hopefully create a mechanically reliable connection that also supports electrically sufficient performance. And the amount of travel that is created during that mating cycle is referred to as wipe, or effective wipe if you're using isolated non-functional paths at the very edge of the free side, like the picture on the lower left. And we need to make sure that we guarantee a reliable mechanical connection is made, but the effective wipe that's left over sometimes acts as an electrical stub that often degrades the performance of the interface, especially at high frequencies. And the mechanical tolerances associated with determining the insertion of the free side and fixed side make up the longitudinal tolerance stack-up. But equally important, shown in the picture on the right, is the lateral tolerance stack-up, where the fixed side can deviate to the left or right of the free side contact. So all of these critical dimensions come together in the respective specifications for each of the form factors to detail how the fixed and free side components are held in place when the two sides are mated together. And the first presenter shared quite a bit of detail and pictures for the free side components. So I wanted to make sure we highlighted and paid some attention to the fixed side components as well. So I put together a series of close-up images to show just how different each of these form factors are underneath the cage, starting with SFP and that product family, the one-lane interface, which is a set of contacts on a 0.8 millimeter pitch. And not pictured, but we did talk about it earlier, is the DSFP form factor, which is a two-lane interface that fits essentially into the same package as the SFP products. QSFP is a four-lane interface on that same 0.8 millimeter pitch. And then QSFP-DD packs an additional row of contacts in that same package width to create an 8-lane interface. You can see in the picture the added depth needed by that additional row of contacts, which forces the legacy, the existing QSFP contacts, to wrap up and over as well as down and around the new high-speed pairs. And then lastly, OSFP is also an 8-lane interface, slightly wider and larger than the QSFP-DD. The additional width isn't twice the QSFP-DD or QSFP form factor, though, and that's because the contact pitch is actually reduced down to 0.6 millimeters. And we did mention OSFP-XD, which is a newly under development standard, and that combines the 0.6 millimeter pitch of a traditional OSFP with the double row of contacts like the QSFP-DD solution. So given the discussion already about the need to go faster and faster, as well as what I just mentioned regarding the importance of the mechanical interface in these solutions, I wanted to highlight the impressive evolution in electrical performance for the pluggable I/O interfaces. So I'll define the pluggable I/O interface as that mechanical mating interface plus the connector body, as well as the attachment to the PCB shown in the picture at the top. And then the graph shows the insertion loss of that pluggable I/O interface across frequency, plotted by target data rate examples, 10G, 28G, 56G, 112G. And the graph shows how we have really squeezed every possible micrometer of performance out of the interface to take us all the way from 10 gigabits to hopefully 200 gigabits. And the key thing to look for here is when the insertion loss profile starts to roll off sharply. A somewhat useful metric is to note when the profile crosses the 1 dB threshold, especially with respect to the Nyquist frequency of that data rate. So the 10 gigabit example crosses 1 dB around 16 gigahertz, well above the 5 gigahertz Nyquist. And then looking at the 112 gig example, that crosses the 1 dB mark closer to 28 gigahertz, just above the 26.56 gigahertz Nyquist. So not as much margin, certainly, as we've evolved to higher and higher data rates. And the technology advances in component design and material properties have certainly contributed to this improvement in performance. But one of the most significant factors has been the improved manufacturing processes, enabling those mechanical tolerances at the mating interface to be much more tightly controlled. And I also wanted to point out that the examples in the graph are not limited to specific form factors. There are both one-lane 112 gig solutions as well as 8-lane 112 gig solutions in the market today. So SFP, for example, has been with us kind of along the entire journey of this evolution. OSFP is a much more new form factor, but the new density challenges actually bring somewhat new problems when we're controlling tolerances across the entire breadth of that port. And the pluggable I/O that we've discussed so far is great for making connections box to box, but connectors and cables have also proven very valuable inside the box as well. The same importance exists inside the box with these types of solutions, providing interconnect that avoids long, lossy PCB routing or avoids significant number of connector transitions inside the box. These form factors are generally a little bit different than the box-to-box form factors we've discussed earlier in this talk, but they still tend to be available in 4 and 8 lane interfaces. And actually, these solutions have often already pushed density requirements to 16 lane and beyond, which is where pluggable I/O is trying to get to today. And I've shown on the screen here a couple of examples of 2 connector cable systems used heavily in server and storage applications today. One on the left is an older generation solution, while the one on the right represents a generational improvement in terms of the target market application. And in this space as well, the need to maintain or increase density while reducing overall footprint and improving electrical performance exists here with these solutions. So in terms of next generation, we've talked today about advances in the form factors and their performance, as well as potentially evolving system architectures. From a market perspective, there's still pressures to enable cost-friendly interconnect and always keep power consumption at a minimum, both of which tend to point to passive copper solutions. But in that respect, we've pointed out that there are shrinking cable lengths when you start to go at faster and faster data rates. And the increasing product densities often add routing complexities and tend to limit any reduction in the physical lengths that would be needed for the interconnect to support these lengths. And there are also limited opportunities now, as you've seen across the evolution of data rates and the connectors that support those data rates today, to further tighten the tolerances and clean up the mechanical interface even further with these form factors. And in terms of PCB materials as an alternative to the interconnect with connectors and cables, PCB materials are certainly improving, but probably not fast enough to solve the problem by itself. So this leaves us with a kind of a dilemma in terms of what we do next for cables and connectors, as well as system architectures. And the solution actually might be to add more interconnect. So I wanted to close with an introduction of a term that I've been promoting called cabled host. These types of implementations are not by themselves brand new, but the performance requirements of the channels at next generation speeds are creating even more benefits for adopting this type of system design. And so the thought is that you would combine some of the dense, low profile connectivity of the inside the box solutions with panel mounted versions of the pluggable I/O connectors that would connect to the same passive or active copper cables or optical modules that we talked about earlier in the discussion today. And so that connection point could be next to the chip or possibly integrated into the chip package to create an optimized path that would be needed to support these next generation data rates. I've shown that kind of on the picture on the right there. And these components that would be used to make up the cabled host would really help resolve a lot of the challenges that I had mentioned on the previous page. So this is one of the directions that we're certainly exploring as an industry. And I think this also highlights the critical importance of connectors and cables as we move forward. And with that, I will pass it back to Tim.
Great, thanks, Sam. So just a real quick summary, then we'll jump into the questions. We've got a few of them coming in. While we go over the summary, please, this is your last opportunity to get your questions answered. So please take a minute to get those submitted. So we saw in the presentation that pluggable connectors come in a variety of size and lane widths. It seems like there's a lot of acronyms out there as well by this presentation. LR, FR, SR, all kinds of things like that. They stand for things, long range, short range, and stuff like that. We've got interconnects are also optimized for the reach. So we see in a lot of the smaller data centers or small reach, that's where the copper is going to be utilized. And then in the long haul, that's where we go to the opera. The more expensive the optical, the longer those reaches are going to be. There's a variety of interconnects and signal modules. So these need to be discussed when you're looking at your data center reach and seeing how far that you need to go and which copper or optical cable will best meet that as far as cost optimized. And then as I was kind of talking about all the different acronyms, and there's a bunch of stuff for this. We covered for deciphering the cable and transceiver types, lengths, and things of that nature. We also went over some of the typical use cases and saw some of the large data centers where some of these are actually being implemented. With that, we just want to jump into the questions real quick. So the first one that we have here, 25 gig is an industry consolidation on one of the three options. Is the industry consolidating on one of the three options? So that's the question. On 25 gig, is there one that's being consolidated on more than the other? That might be a question for either
I think that refers to the FEC, the CALSN. Is that correct?
I would interpret it as the three different PHY types. I would say that the early adopters and first products came to market with the Ethernet Technology Consortium 25 gig version. More recent products available in the market are supporting, and for the majority, both cases, the IEEE modes as well as the 25 gig. And I would predict that with respect to time, that it will be the IEEE 802.3 25 gig modes that will become the long-term incumbents for 25 gig Ethernet.
Great. Let's get on to the next question here. What's the latency difference between active and passive DAC cables? And they have in parentheses here, PAM4 encoding, question mark.
Brad, do you want to take that one?
Yeah, sure. So when PAM4 first came out, everybody was like deer in the headlights. What are we going to do with this? So a lot of people just for an active DAC, they put in a DSP. And that put in somewhere around 80, 90 nanoseconds of delay, latency delay, as the computer basically load, fetch, store, compute, put back in memory, that kind of stuff, to compute the algorithm to find the signal and the noise. The next generation that's come out is using, and also people put retimers in there, which just kind of cleans up the signal and gives it a little bit of a boost. But they're different reaches and different requirements, whether you need FEC or not. The next generation uses a pre-emphasis type chip that is very low latency. It's on the order of less than 20 nanoseconds, and is somewhere close to just about 1.5 watts per end. The DSP typically drew about 2.5 per end. So if you had you'd have 5 watts for a cable. But it looks like that the next generation is down in the 15 to 20 nanoseconds and 1.5 watts. So it's much more tolerable.
We do have a couple more questions coming in. We'll have to get those answered in our blog. Just want to spend the last minute that we have here just to go over a few things post webcast. As a reminder, please give us a rating, provide any feedback that you can, and help us improve these. If you're looking for a copy of the slides, they'll be available at the SNIA Educational Library. You'll see the link right there. Also, as a reminder, all the Q&A from this webcast, including the answers we couldn't get to today, will be posted on the SNIA blog. So that's going to be in the NSF forum inside the blog section there. And as a reminder, follow us on Twitter. And there are also some additional content up there on SNIA if you guys want to further your education. So I encourage you to look at the SNIA website and look at what you can find there. Again, thanks to our presenters doing a great job today. We're going to get this wrapped up, it looks like, just on time. And thank you for everybody who attended as well.